Hi guys, good morning. Today let us see about the one more algorithm design technique called as dynamic programming. So as we know, the algorithm design technique means the way of approaching to solve the problem. Okay, so let us consider there is a problem. So to solve it like a recurrence way. Okay, and in the case of dynamic programming, the general idea here is instead of directly attempting to solve the big problem, first consider a sub instance, that means a small subproblem. First solve it, then record the result of the smaller sub instance or smaller subproblem. Using that solution, you can get the solution for next bigger problem, that means somewhat extension of the smaller one. Again, so this procedure will be repeated several times so that to get the solution for big problem. You can observe the main idea here. So first of all, we need to set up the recurrence relation. That means what is meant by the recurrence relation means something, some procedure should be common for every iteration. So that is what we call as a recurrence procedure. So something you are doing recursively executing, it means repetitively executing something. Okay, but the size of the problem is different. Okay, first time you may take the smaller instance, then solve it, then record the solution for the smaller instance. Then by using this solution, you can solve the next instance, that means somewhat bigger. But how you are getting the solution for the next one means that is from the help of the previous solution and executing the same procedure which you followed for the smaller instance. Okay, this is the general idea of the dynamic programming. In fact, it was invented by an American mathematician called as Richard Bellman. Okay, so let us see one example called as a Fibonacci numbers. I think you know that already, the Fibonacci series, like starting from 1 and 0 instances, and with the help of these two you can get the like f of 2 is equal to 0 plus 1. Similarly, f of 4 is equal to f of 3 plus f of 2, and so on. So in general, if I want to compute the f of n, I want to first find out f of n minus 1 plus f of n minus 2. Similarly, I want to find f of n minus 1, I have to go for f of n minus 2 plus f of n minus 3, and so on. That means, why I am giving this example as the dynamic programming example means, so here how to solve the problem of size n with f of n, that is the question. So to solve the problem f of n, instead of directly attempting to the f of n, I can solve it from the scratch. That means I can take the smaller instance f of 0 and f of 1. These two smaller problems results, that is 0 and 1, are recorded. Now by using these solutions, these smaller instance solutions, I can get the solution for f of 2. So f of 2 is equal to this 0 plus 1. Then after finding f of 2, the result will be recorded somewhere in some data structure. Then you can go for next level, that is f of 3. So like this I can reach f of n. So that means this is what we call as a dynamic programming approach of solving a problem. Okay, now let us see two more. We can say this is what I was explained. Okay, that is starting from f of 0 equal to 0 and f of 1 equal to 1. Similarly, f of 2 I can find out. So as long as I can proceed the f of n. Okay, so like this I can proceed it. Now you can see the two more well-known algorithms well-known problems we can solve with the help of the dynamic programming paradigm. The one is called as to find the transitive closure of a graph. To find the transitive closure of a graph, or we can say a matrix. Similarly, what is how to solve all pair shortest path problem. In fact, there are corresponding solutions. The first, to find the transitive closure, the algorithm name is called as Warshall's algorithm. So the Warshall is the name of the author, so who invented this algorithm. So the name itself called as Warshall's algorithm for transitive closure. Similarly, the Floyd's algorithm for all pairs shortest path. Okay, here also the Floyd's is called as the author name. Okay, let us see these two problems. In fact, these two topics are given as assignment, so the advice is to listen carefully and try to solve the assignment questions by yourself, which I was already uploaded in the SmartCamp portal. Okay. Let us see the first problem. The first problem is, given a graph, or we can say a matrix, how can I find the transitive closure? Now, first of all, what is meant by the transitive closure? The transitive closure of a graph means the existence of all paths in a digraph. Existence of all paths in a digraph. The digraph means in the graph where the edges have directions. Okay, the edges has some directions like this. Okay, directions. Now, what is meant by all paths? What is meant by all paths? Let us see this figure. The first figure, there are 4 vertices, 1, 2, 3 and 4, and there are 4 edges. 1 to 3 there is an edge, 2 to 1 there is an edge, 4 to 2 there is an edge, 2 to 4 there is an edge. Now, if I take the matrix, if I write a matrix in terms of like this, so I can write 1 and 2 and 3 and 4. Similarly, 1 and 2 and 3 and 4. Now, what is 1 to 1? If there is a direct edge, or we can say if there is a path. Okay, so because there is a 1 to 1, so there is no edge between 1 to 1, so I can indicate it as 0. Then 1 to 2 there is no edge, so I can indicate it as 0. 1 to 3 there is a edge, so 1. Then 1 to 4 there is no edge, so 0. Similarly, 2 to 1 there is an edge, so 1. 2 to 2 no edge, 0. 2 to 3 no edge, 0. 2 to 4 no. 2 to 4 there is an edge, so 1. 3 to no edges, so all are 0. 4 to only one edge is there, 4 to 2 remaining are zeros. Okay, but how can I, but if you observe here, even though there is no direct edge between 2 to 3, but I can move via 1. Okay, that is the meaning of all paths. That means even though there are no direct edges, how can I find if there is a path via intermediate vertices? Okay, that is the meaning of existence of all paths in a digraph or the transitive closure. Okay, so in fact this is the result. By applying this Warshall's algorithm we will get. That means if you observe here, there are 5 new ones are added. Why these new ones are added? If you observe here, this is called as 2 to 2. 2 to 2 there is no edge, but I can start from 2, I can go to 4 to 2. That means via 4 there is an edge, so I am adding it. Similarly, 2 to 3. 2 to 3 there is no direct edge, but I can go via 1. Similarly, 4 to 1. 4 to 1 there is no direct edge, but I can go 4 to 2 to 1. So 1. Similarly, 4 to 3. 4 to 3 there is no direct edge, but I can go 4 to 2, 2 to 1, 1 to 3. So there is an edge. Similarly, 4 to 4. 4 to 4 also there is no self edge, but I can go 4 to 2 and 2 to 4. Okay, so this is, it means we have to explore, is it possible to reach from one vertex to another vertex via intermediate nodes. Initially we are taking without any intermediate vertices. Okay, later we will add one by one. That means first we will add with one vertex. If I add vertex 1, is there any intermediate? It means if I add 1 as the intermediate vertex, is there any paths or new paths are available? If I adding 1 and 2, is there any new paths? If I adding 1, 2, 3, is there any new paths? If I adding 1, 2, 3, 4, is there any new paths? Okay, so that is the meaning of transitive closure or Warshall's algorithm. Okay, let us move it. This means what I am going to do is, suppose there is an edge called as I and there is an edge called as J. If there is a direct edge, between I to J, we are directly indicating it as 1. That means the path is possible. Suppose if there is no direct edge, we have to check that is there any path via intermediate vertex. That means when it is possible intermediate vertex, if these two are true, that means there is a edge between I to K as well as K to J, then I can conclude that I to J is possible via K. Okay, so to find it, this is the core algorithm in the case of the Warshall's algorithm. That means I have to go step by step. In fact, here, so how the step by step means, initially I am considering 0 number of vertices, then I am considering with one vertex, then I am considering with 1 and 2 vertices, then I am considering with 1, 2 and 3 vertices, then I am considering all vertices. Okay, so this is the way. That means initially I am taking the initial solution with R0 with K. Here K indicates that the number of vertices are taking as intermediate vertices. So initially R0 of Ij means, that is what we recorded. This is the initial matrix. Now from this we have to find out R1. How can I find the R1 of Ij? That means if it is previously there is a 1, it's no issue, we can leave it. Otherwise we have to go for, is there with via intermediate vertex, is there any path? We have to check it. Is there any path via intermediate vertex? Let us see an example. We can better understand about this core algorithm. Okay. Now I am taking the same problem, that is 1, 2, 3, 4. Now initially I am taking the initial matrix. What is the initial matrix? That is, if there is a direct edge, there is a 1, otherwise there is a value 0. Now I want to find the R1. I want to find out R1. What is meant by R0? Means 0 number of intermediate vertices. Without any intermediate vertex, what is the path is available? So direct edge. If there is a direct edge, 1, otherwise 0. Now I want to find out, is there any path via if intermediate vertex has 1. So I want to check that how can I find R1. To find R1, I have to use the solution of R0. That means this is what we say the dynamic programming. To get the solution for next level, use the solution of the previous level which was recorded in some data structure. Okay, that is what we say the dynamic programming. Okay, now I want to check that This is called as actually 1 1. Now I want to check that 1 1. So R1 1 1 is equal to R1 1 1 is equal to R 1K plus R K1. This is 1 R war R 1 1. Suppose if R1 1 is already equal to 1, don't worry. But if it is 0, if it is 0 means what? There is no direct edge. But look for, is there any path between R11 via K? Via K means what? 1 to K I am going, then K to 1 I am coming. Now what is K? That is 1. The K is 1. So is there any path via 1? So R11 plus R11. What is R11? 0. R11 0. So 0 plus 0 you are getting only 0. So no need to update the value, that is 0. Okay. Or let me explain one simple shortcut for this. Take the first column, take the first row, first column and first row. Take the element column wise, apply it to whole row. Then take the second element column wise, apply it to entire row. Then take the third element, apply it to entire row. Then take the fourth element, apply it to entire row. That is a very simple shortcut to apply Warshaw's algorithm. Okay, now let us see how to apply it. So 0 and same row 0, 0 plus 0, 0 over. Then same element, column element same, row 0 plus 0, 0. Already 1 is there, put it as it is. Otherwise you can apply it also. Okay, see, if it is already available, don't touch it. Otherwise you can apply this addition. Then 0 plus 0, 0. Now observe the second element with same row. Now you will get some clarity what is going to happen. Now already 1 is there, leave it. Okay, next second element means 1 plus 0. 1 plus 0 means 0. Then 1 1, existing is 0. Now 1 1 means 1. So we can put here. That is 1. Next 1 0. Already 1 is there, so you can keep here. Now you can observe here why you are getting this 1 here. What is the meaning of this extra 1 you are getting here? In fact, this is 2 and 3. 2 to 3 there is no edge, but I can go 2 1 1 3. This is 2 1. This is 1 3. That means 2 to 3 there is no edge directly, but I can go 2 1 and 1 3. If both are 1 1, so that I am adding 1. Suppose if it is 0 here, I should not put. So I have to do, if both are 1, then only I can mark it as 1. Okay, like this I can. Next time I can take the third element in the column and apply it to row. 0 plus 0 0, 0 plus 0 0, 0 plus 1 0, 0 plus 0 0. Then I can take the fourth element, 0 plus 0 0, 0 plus, already 1 is there means don't do the addition. First put the ones as it is. Remaining cells you can do this addition. 0 plus 1 0, 0 plus 0 0. Okay. Now let us see from this how to get this option here. Okay, now what is how to get this? See, this arrow mark indicates that to get the result of R1, this rows, this column and this row applied. Again, what is this column and row indicates that to get the result of R2, this column and this row is applied. Okay, take the column element, first element, apply it to one row, you will get 4 values. First, take the second element in the column, apply it to row, you will get these 4 values. Take the third element in the column, apply it to row, you will get the third row. Take the fourth element and apply it to row, you will get this row. So first 3 no change. Now let us see the fourth one, you will get the clarity. I am taking fourth element here 1, applying it to row 1 1, but actually it is 0 here. Now I am applying 1 1. So 1 1 means I want to replace 0 by 1. Then 1 is already available. Then this one 1 1 1. Then 1 and 1 1. So in this way I have to proceed again from R3 and again from R3. See why I am stopping at R4? Because there are only 4 vertices. Suppose if there is a 5th vertex also in the graph, I have to proceed till R5. What is the meaning of R0? Means 0 number of vertices as intermediate. R1 means only 1 vertex as intermediate. R2 means 1 and 2 vertices as intermediate. R3 means 1, 2 and 3 as intermediate. R4 means 1, 2, 3, 4 all are as intermediate. Okay, hope you might understand about the Warshall's algorithm. Try to solve the examples which I was given as assignments. Okay, the same thing, just notation represented here in terms of which are the which are the edges newly added in the graph step by step. Okay, the same algorithm, just this is the core component. Okay, now let us move to the next algorithm called as Floyd's algorithm. Okay, now once again this is also similar to that one, but here the objective is how to find the shortest path between all pairs in the graph. Suppose 1 2 3 4, these are the 4 vertices. Now I want to find out what is the shortest path. What is the shortest path between any two? For instance, I can see between 2 and 3 there is a direct path 6, there is another path 1 plus 4 2 1 3, there is another path 2 4 and 3. That means there are 3 paths totally between 2 to 3. One is direct 2 to 3 6, 2 to 1 1 to 3 5, 2 to 4 4 to 1 3 plus 1 4. So which is the shortest path? The 4. Okay, so like this I want to find out the shortest path between all pairs, all pair of vertices. That is the objective of the Floyd's algorithm. Okay. Again the procedure is same. That means I will start with here, the D stands for distance. I will start with D of 0. That means if there is a path I can mark it as 4. That means there is a wedge. Yeah, it means direct edge. If there is no direct edge, I can treat it as, there is no direct edge means, because that means I can treat it as infinity. That means there is no, it will take long time, like that, long distance. Okay, then from distance D0 I can compute D1. What is meant by D1 now? I am allowing one vertex as intermediate. Now is there any path? If there is a path means infinity is going to replace by with some value like 4 or 5 or something. Okay, that is the advantage. Okay, let us see step by step what is going to happen. Okay, here I am getting this matrix from this graph. what it means. Now 1 to 1, see here the 1 to 1 I am indicating as 0. Why I am indicating as 0 means the distance, because source and destination is same, there is no distance, so it is 0. Then 1 to 2, 1 to 2 there is no direct edge, so infinity. 1 to 3 there is a direct edge, 4. 1 to 4 there is no edge, infinity. 2 to 1 there is an edge, 1. 2 to 2 that is same source and same destination, 0. 2 to 4 there is an edge, 2 to 4 there is an edge, that is 3 in fact, but why it was 4 as it was wrongly entered. Okay, it was wrongly entered. 2 to 3 that is 6, not 4. Okay, 2 to 4 that is 3. 2 to 3 that is 6, not 4. Okay, next 3 to 1 infinity, 3 to 2 infinity, 3 to 3 0, 3 to 4 infinity. 4 to 1, 4 to 1, I think there is a one more edge here. Yeah, I missed it. There is a one more edge between 4 to 1, that is 6, and 2 to 3 there may be one more edge, that is 3. Okay, forget it. Let us see in the example. Yeah, it may be different. Anyway, now I think you got some idea about how to represent each edge. Okay, so here I think one more edge between 4 to 1, that is 6, and here some, okay, some edges missing in this graph. Anyway, it's not an issue. Okay, then now let us see how can I find the shortest path. Here our objective is between I to j, if there is a direct edge some value, if no edge infinity, or 1 to same edge y equal to j means 0. These are the three options. Now we want shortest path. Suppose I want to go from Vellore to Chennai 100 kilometers. Imagine Vellore to Chennai 100 kilometers. Now if I go Vellore to some city x and x to j, if I get 50 and 40, that means 90 kilometers, then which one you will prefer? 90 will be preferred than this 100. That is the meaning of the shortest path. So what we are going to do is initially we are taking only the direct paths, then we have to explore the shortest paths if available via intermediate nodes. So here the K is called as intermediate node. Initially we will add vertex 1, that means with one vertex is there any intermediate path. So that means I can write the equation like this: minimum of direct and this one plus this one. So out of these two, either first one or second one, which is the minimum, that is considered as shortest path. Okay, let us consider an example, we'll better understand. Okay, in the previous slide, if you are not getting any, I think if you are confusing, let us see here once more also. 1 2 3 4, 1 2 3 4, 1 2 3 4, 1 to 1 0, 2 to 2 0, 3 3 0, 4 4 0. Then 1 to 2 there is no edge, infinity. 1 to 3 there is an edge. Okay, actually in fact the values are missing here, the values are 3. Okay, and 2 to 1 the value is 2, and what is this, 3 to 2 7, and this is 3 to 4 1, and 4 to 1 6. Okay, so these are the values in the graph. Assume that these are the values, these are the distance weight. Now we want to find out the shortest one. Now how can I get the D1? Again the same principle which we followed in the versus algorithm. Take the first column and first row. Take the first element in the column and apply it to row. Already available 0. Now 0 plus 0, which is the minimum? Either 0, comma 0 plus 0. Which is the minimum of these two? Of course both are 0, so 0. Next, already available infinity. Already available infinity. Now 0 plus infinity, infinity. So infinity. Then already available 3. 0 plus 3, 3. Both are same. Already available infinity, 0 plus infinity, infinity. Next, take the second element, apply to row. Already available 2. Now 2 plus 0, 2. Both are same. Again, already available 0. Now 2 plus infinity. 2 plus infinity, infinity. Which is the minimum? 0 and infinity, 0. Then already available infinity. Now 2 plus 3, 5. So which is the minimum? Either infinity or 5. So 5. Now you got the clarity. Then already available infinity, 2 plus infinity, infinity. Similarly, take the third element. Infinity plus 0, infinity. Already available 7, infinity and infinity, 7. Already available 0, infinity plus 3, 0. Already available 1, infinity, infinity, 1. Then this one. Now already available 6. Now take the 6 plus 0, 6. Already available infinity, 6 plus infinity, infinity. Infinity, 6 plus 3. Here observe. Already available infinity. Now 6 plus 3, 9. So infinity, comma 6 plus 3, 9. So infinity and 9, which is the minimum, you can take 9. That means 0. See, why you are getting these two are extra? Observe here, 2 to 3. 2 to 3 there is no direct edge, but if I am adding this one vertex 1 as intermediate, I can get the path with the distance as 5. That is 2 1 and 1 3, that is 5. Similarly 4 to 3. 4 to 3 there is no direct edge, initially infinity, but I can go, if I am adding 1 as intermediate vertex, so I can get 4 to 1 and 1 to 3, that is total distance as 6 plus 3, 9. Okay, like this we have to proceed. Similarly, you can see the D2. What is meant by 2? 1 and 2 both are as intermediate vertex. Here you are getting 9 as extra value, remaining all same. How you are getting this 9? 3 1. 3 1 there is no direct edge, but I can go via 2. 3 2 2 1. 3 here 2 means what? I can observe 1 and 2 are intermediate vertices. So 3 2 2 2 1. So 7 plus 2 9. Similarly, what is this? What is meant by this 10? I can add here, first of all 3 means 1, 2 and 3. 3 vertices as intermediate. So 1 to 2. 1 to 2 there is no direct edge, but I can go 1 to 3, 3 to 2. So 3 plus 7, total 10. Okay, so this is the procedure to obtain the shortest path. So finally you can observe this. This is the solution to get the solution. So this indicates that the shortest path between the pairs. Now you got the idea about the dynamic programming. So here the dynamic programming, the concept is, instead of solving the problem entirely straightforward, we can take the smaller instance. That means smaller instance means here we are not considering intermediate, any vertex as intermediate. So we are taking direct edges initially. Then by adding 1 as intermediate vertex, from this you can get the solution as this, from this you can get the solution for this. Then add the 1 and 2 as intermediate vertices, then add the 1, 2, 3 are intermediate vertices, then add the 1, 2, 3, 4 are intermediate vertices. Okay. So this is an algorithm. The main important equation we need to consider as this one. That is, suppose I want to dij, I to j means you can consider minimum of direct distance and minimum of with intermediate vertex as k. If which one is minimum, that is considered as the shortest path. Okay. Hope you might understand. Okay. So try to solve the assignment problems and proceed further. Thank you.